Hello everybody. So today we'll be starting with the analysis of faults in a power system. As we know that the power is transferred from the generator to the load through a transmission line. In normal operating conditions, the amount of current that flows through the transmission line depends upon the rating of the loads, how much amount of real and reactive power the load requires for its operation. Now, any disruption of this normal operation or the normal flow of current occurs when a fault happens. Uh, Fault can be of two types, symmetrical and unsymmetrical. The symmetrical three-phase fault involves all the three phases of the transmission line, whereas the unsymmetrical faults does not involve all the three phases. It may involve one or two of the phases. The current flowing in the network after the fault depends upon the following conditions. The internal EMF or the voltage source of all the synchronous machines such as generators, etc. in the network. This current, the current that flows after the fault happens, has three distinct components. The current flowing immediately after the fault, which is called the subtransient current. We'll come to that later, how the subtransient current flows or what factors are involved in the flow of the subtransient current. Then the current flowing a few cycles after the fault is called a transient current, and the sustained value of the current which flows after uh, more cycles than that of the transient current is called the steady state value. The steady state value is always less than the subtransient and the transient values of the current. All this differs significantly because of the effect of the armature flux and the inherent RL circuit characteristics of the machines to a voltage source. So these currents depend upon the uh, value of the internal impedance of the voltage sources, the line parameters, and maybe some other factors. Uh, the impedance in the network between the synchronous machines and the fault also plays an important role. It is also required to measure the impedance of the network between the synchronous machines and fault for proper relaying function, which we'll be studying in the chapter of relays. Now, what are the causes of the symmetrical three-phase faults? The causes of the symmetrical three-phase faults may be one of the following: insulation failure of the equipment, flashover of lines initiated by lightning strike, accidental faulty operation. So insulation failure, we have studied what insulation failure consists of and the flashover of lines in Power System 1 in 5th semester. So those are the major causes of symmetrical three-phase faults. And another cause is accidental faulty operation, which may occur due to natural or manual accidents. The protection of the equipment from the heavy current flowing during faults is of paramount importance, and that is very clear. You can understand that the equipments have a certain power rating and they can handle up to a certain current. Now, when a short circuit symmetrical fault occurs, heavy current flows through the circuit, and the equipments, most of the equipments that are connected to the line, may not be able to withstand that heavy amount of current. So, if you want to stop the damage that may happen to the instruments, then we have to take proper measures so that the faulty part of the system is isolated from the rest of the system. Now, to disconnect the faulty part from the rest of the system, we need some protective relaying and circuit breakers. Now, when we are going to implement this protective relaying and circuit breaker system, then we need to know that what is the maximum amount of current that may occur in the system in case of a fault. This knowledge will help us to decide the ratings of the relays and circuit breakers that we have to use for protection. So that is the scope of fault analysis to acquire knowledge about the magnitude of currents that would flow under short circuit conditions to determine the rating of the circuit breakers and relays. The short circuit symmetrical faults, which involves all the three phases, are very rare, but they are the most severe types of fault. That means when a short circuit symmetrical fault occurs, then the current that flows through the line is much higher compared to the unsymmetrical faults, which comprises of single line to ground or double line to ground fault or line to line fault. These are the three types of unsymmetrical faults: single line to ground, double line to ground, and line to line faults. But the symmetrical three-phase faults are much more severe compared to these unsymmetrical faults. When we analyze a circuit for uh, fault, we can we can neglect the loads. The loads can be neglected as the voltage dips so low in case of a fault that the current drawn by the loads is very less, is negligible compared to the fault currents. So for better calculations and for ease of calculations, we can neglect the amount of current drawn by the load in case of a fault. Now next, we'll be going to the transient on a transmission line. Now you can see that here we have a generator, a voltage source, whose instantaneous voltage is given by root 2 V sine omega t plus alpha, where uh, V is the root 2 V is the maximum voltage that can occur in the line due to the source, and this is the sinusoidal. Now, as I was saying, that here we have got a voltage source. This is its maximum voltage root 2 V, and this is a sinusoidal component which has a component alpha which determines at which point of the voltage waveform the fault has occurred. The fault can occur at any point between 0 to pi. This is the resistance and the reactance of the line. We have neglected the internal impedance of the voltage source. This is a switch, and this can be considered as the fault position. The load has obviously been neglected, as it was told earlier, that in case of a fault, the current flowing into the fault is so much that the current drawn by the load is negligible. As the fault point voltage is very low, so the current drawn by the load from the fault point voltage is also very low. So the load current is negligible compared to the fault current. Most of the current will flow into the fault. Now the short circuit is assumed to take place as t equal to 0. As I have said, the parameter alpha controls the instant on the voltage wave when the short circuit occurs. Now using KVL for the above circuit, we can write root 2 V sine omega t plus alpha is equal to Ri plus L di dt. The switch can close the circuit at any instant, and the phase angle can have a value between 0 to 2 pi radian. The complete solution of the equation 1 is the sum of the general and particular solution, that is IT is equal to IHT plus IPT, where IHT is the general solution and IPT is the particular solution. We have already done this solution in circuit theory, but we'll recap the solution once in the power system scope. To find the general solution of the differential equation, we have to solve the characteristic equation of the homogeneous differential equation, which can be given by Ri plus L lambda I, where lambda is the eigenvalue of this equation, characteristic equation. Now, if we take I is equal to e to the power lambda t, so di dt or I dash is equal to lambda e to the power lambda t. We replace this value of I and di dt in the equation 1, and in this equation actually, and this gives us L lambda e to the power lambda t. Actually, I am replacing I is equal to e to the power lambda t in this equation 2. So we are getting this value. So from here you can see that lambda can be value of lambda can be calculated as minus r by L. So the general solution for equation 1 is IHT is equal to C1 e to the power minus r by L into t, where C1 is a constant which can be obtained by considering the initial values of the system. The particular solution is found by substituting in equation 1 a general expression of the current which is given by IPT is equal to A sin omega t plus alpha plus B cos omega t plus alpha. Now if I differentiate this IPT, will get omega A cos omega t plus alpha minus omega B sin omega t plus alpha. Now we'll replace IPT and dip dt in this equation 1 in place of I and di dt. So by replacing those values, we are getting these two simultaneous equations. We replace the values and then we compare it on the with the right hand side. We compare the left hand side with the right hand side. So obviously in the right hand side we have got a sine component but no cos component. So we can compare the coefficient of the sine component of the left hand side and equate it with the coefficient of the sine component of the right hand side. But as there is no cos component on the right hand side, so the coefficient of the cos component of the right hand side is 0. So we can equate the coefficient of the cos component of the left hand side to 0. So we get two simultaneous equations, which is Ra minus omega Lb is equal to root 2v and Rb plus omega La is equal to 0. Our objective is to find out the values of A and B, so that by putting the values of A and B in this equation 4, we can find out the actual solution of the general expression, particular solution of the current IPT. Now solving the simultaneous equation, we get the values of A and B. Here we can see that the value of A is equal to EMR by R square plus omega square L square, where EM is equal to root 2V as was given in the previous diagram. Similarly, by putting the value of A in one of the equations, we can find out B as B is equal to minus EM omega L by R square plus omega square L square. So putting the values of A and B in the equation of IPT, we can get this value. We take root 2V by root over R square plus omega square L square as common. The reason behind that is that we want to give this equation a form of sine A minus B, a form of sine A minus B. So now we have got a sine component and a cos component. Now what does these two mean? These two can be obtained from our impedance diagram, where R is the base, omega L is the perpendicular, and hypotenuse is root over R square plus omega square L square. Theta is the angle here. Now we know that theta is equal to tan inverse omega L by R, and sine theta is equal to omega L by root over R square plus omega square L square, and cos theta is equal to R by root over R square plus omega square L square. Now here we can replace sine theta in place of R by root over R square plus omega square L square, and cos theta in place of cos theta in place of this value and sine theta in place of this value. This will give us IPT is equal to root 2V by root over R square plus omega square L square within bracket cos theta sine omega t plus alpha minus sine theta cos omega t plus alpha. We can consider that this is A and this is B. We get root 2V by root over R square plus omega square L square sine of A minus B. And here theta, we know that theta is equal to tan inverse omega L by R. So sine of omega t plus alpha minus tan inverse omega L by R. This is sin A cos B minus sin B cos A. So this is A and this is B. So we get sin A minus B. Now the complete solution is the summation of the general solution and the particular solution. The general solution was obtained by IHT is equal to C1 e to the power minus R by LT, which is exponentially decaying function, and the particular solution value was obtained here, which gives us root 2 v by root over r square plus omega square l square sine of omega t plus alpha, which is a minus theta, which can be replaced by tan inverse omega l by r. To get the value of the constant C1, we can consider the initial condition. The fault has occurred at the initial condition of t is equal to 0. To get the value of C1, we put t is equal to 0 in this equation. So obviously e to the power minus r by l into t, here t is equal to 0. So this will become 1, and root 2 v by root over r square plus omega square l square sine omega t, this becomes 0, omega t value becomes 0. So we are left with alpha minus theta, and this is equal to 0, as I0 is equal to these two values, which can also be considered as the transient and the steady state value. We'll be seeing that in the current diagram, current waveform diagram, why it is called such. So it is called the transient and the steady state value, and at t is equal to 0, the current is 0, being the inductive circuit. This is an inductive circuit. So C1 is equal to minus of root 2 v by root over r square plus omega square l square sine of alpha minus theta, which gives us root 2 v by root over r square plus omega square l square. This will be reversed if I take the sign, negative sign inside, then sine of theta minus alpha. Thus the short circuit current becomes a summation of these two components, where one is an exponential decaying component and the other is a sinusoidal component. This sinusoidal component is called the symmetrical short circuit current or the steady state component, and the DC offset current, that is the exponentially decaying current, is called the DC offset current, which is also called the transient component. So this is a waveform. This was the original waveform. We can see that this is a voltage waveform and this is a current waveform. The phase difference between the voltage and current waveform is theta. This is the point of occurrence of fault, and this is the zero crossing. So from the zero crossing to the point of occurrence of fault, the angle is alpha. So this fault can occur from anywhere between 0 to 180. So alpha can have a range of 0 to 180. This is our DC offset current, which decays with time. The DC offset current, e to the power minus r by l into t, decays with the time constant. The combination of these two, the symmetrical current and the IT, this gives us the total current in case of a fault. This is the transient component, the DC component, and this is the symmetrical component. So from starting from the subtransient component, crossing the transient part, we go up to the steady state value. So you can see that once we have reached the steady state value, the DC offset current has died down and only the symmetrical steady state current is there. So this part can be called the steady state current. Now this is the maximum momentary current which occurs immediately after the fault happens. This maximum momentary current can reach up to twice the value of symmetrical steady state current. We'll come to that later. How to calculate the value of the maximum momentary current, we'll come to that in the next class. So this is another diagram where you can understand it clearly. This is the current in per unit value, and this is the time in second. So as the time increases, the exponential component decays, and the symmetrical component or the sinusoidal component, which is symmetrical steady state value. So the same thing is written here. We can see that the second part of the equation 8, which contains the term exponential minus r by lt, damped out. This is called the DC component. The current shown in the figure is called asymmetrical component, asymmetrical current. Obviously, this is asymmetrical current because on one side of 0 it has a full value on the positive side, on the negative side we have less value, where a symmetrical current should have equal positive and negative values in the positive and negative half cycles. When the current reaches steady state, we call it symmetrical current. The asymmetrical current can reach a peak value of nearly twice that of symmetrical current, which is called the maximum momentary current. So our circuit breakers relays should be calibrated or should be chosen such that the ratings are capable of withstanding the maximum momentary current or the asymmetrical current forming just after the fault happens, which can obviously reach a peak value of nearly twice that of symmetrical current. So this is up to this uh, is for today. In the next class, we'll be continuing with the different aspects of the symmetrical fault, and then we'll move on to the unsymmetrical faults.